So if you can share my screen. Okay, guys. So yes, let us start. Welcome again. Thank you for joining. So today's lesson will be on physics. For the past few lessons, we've been doing mostly chemistry. So we've done empirical formula, we've done percentage yields, and so on. So now we are entering the physics section. So the way it starts is on this particular section, vectors and scalars. So what we want to achieve after this lesson is done, you should be at least able to list physical quantities, for example, time, mass, and so on. And most importantly, you should be able to define and differentiate or tell the difference between what's a vector and what is a scalar quantity. And then part of what we'll do are exercises that will help us calculate what we call resultant vectors using a very specific method called the tail to head method. Tail to head, right? That's what they call it. You'll see why it's called that. And let us start. Now, let's do this. Great. Started on the wrong page. It's fine. Not sure it's okay. Oh, yeah, much better. Now, so let's start on a basic, the most basic. Let's do this. So let's start on the most basic definition. A physical quantity, right? You don't necessarily need to know the definition of what a physical quantity is, at least not officially, because you will never be asked what that is in an exam. But just to give you a brief idea, when we talk about physical quantities, we're talking about any measurable aspect of the physical world. Right. What do I mean by that? Anything that you can measure in this current reality. So basically, we're talking about if you've heard someone saying, "Oh, I am 5'4". Okay, that's what Americans say, but we would typically say I'm 1.2 meters tall, or I am 1 meters tall, and so on and so forth. That's a measurable aspect of the world. It's a height. So that's what physical quantities are. You can also measure what you call time. You can also measure your mass. People who like doing bathroom scales, you're on a weight loss journey. You have a bathroom scale at your home. You are measuring mass there. It's not your weight, but it's your mass. As physicists or chemists or aspiring physicists and chemists, you shouldn't talk like normal people. There's a difference between mass and weight, right? But that's not the point. Now, in physics, you have what you call a scalar quantity. So out of all these things I've mentioned, we've talked about there are stuff like heights, mass, time, speed, anything you can measure, basically. So all of these things I've just mentioned, they are usually divided into scalar quantities and vector quantities. Let me create a table for you. Let's see. Scalar quantity This would likely be a 2-mark question in an exam where they say, give us an example or 2 examples of a vector or a scalar quantity. It will depend which one they want. So then you would be able to do that after this lesson. Right. Right now, let's do this. Scalar quantity definition is a physical quantity that only has magnitude. Right. I'll tell you what I mean by that. That only has magnitude. Has no direction. So typical examples of what this is, these are actually, for instance, your height. If you're 2 meters tall, you're just 2 meters tall. There's no direction to that. Right. Your mass. If you weigh 20 kilograms, there's no such thing as saying I weigh 20 kilograms to the east, right? So it's just 20 kilograms. There's no direction to it, only the magnitude. The magnitude being the 20 kilograms. If you can think about it, even time only has magnitude but no direction. If it's 12 o'clock, it's not 12 o'clock to the east or west or south or whatsoever. It's just 12 o'clock. Another example is, okay, maybe let's remove heights and use examples that you'll probably remember. Another example is speed. Right. So if you remember, earlier this year, you were able to define the difference between speed and velocity. Right. So speed and velocity are not the same, even though the units or the SI units are usually the same, but they are not the same in terms of speed is a scalar while velocity is a vector. But I'll tell you what a vector is right now. And then another example is temperature. Temperature is just 10 degrees, nothing else to it. And then later on, you would learn about what you call charges or charge. Basically, either something is positively charged or negatively charged. I think you've probably already covered these. If not, you will later on this year. Now, these are all the typical examples of scalar quantities. So a scalar quantity is any physical quantity that only has magnitude but has no direction, right? So like speed, mass, time, temperature, and charge. Now, vector, on the other hand, is the direct opposite of what a scalar quantity is, or rather in addition to what a scalar quantity is. So this one is any physical quantity right, that has both magnitude and direction. Both. Keyword is both. Magnitude. I think I could have fit this here. Right. And direction. Let me write it in caps. Haha. So it has both magnitude and direction. So remember, from the scalar part, we said a scalar does not have a direction. It only has a magnitude. A vector quantity is the privileged guy. That guy that has both money, and intelligence, right? This guy has both magnitude and direction. Very privileged. Right. So now, what are examples of a vector quantity? Since we've already mentioned speed here, let me just do an example that can match that. So velocity. Velocity, right? How does it have direction? Usually when you specify velocity, you would say something like 20 meters per second east. So I saw an ambulance traveling at about 20 meters per second or 20 kilometers an hour to the east. That's how you describe velocity. Speed, on the other hand, you'd simply say 20 meters per second. You wouldn't specify the direction. So that is the difference between speed and velocity. That's why speed is a scalar while velocity is a vector. I think I have someone whose video is on. You can turn off your video. Don't worry about turning it on. I think it was this Ngomile. You can try turning off your video because it can also waste your data. Just to save your data, please turn it off there. Right. Then another example of a vector. Okay, where's my pen? Good. Another example of a vector is force. Right. So remember when I said you are an aspiring physicist, a chemist, engineer, or whatever. So you shouldn't talk like the general public. So when someone says my weight is 20 kilograms, that is false. That's not weight, because weight is force, and force is a vector. What they're actually describing is mass. Mass, if I say I weigh 20 kilograms, right, that is mass. But if I say I weigh 20 newtons, it means, okay, that's not the point of this example, but weight is measured in newtons. Let's say usually 20 newtons downwards. Down. Right. So your weight is always pointing downwards, for instance. Right. So just a side note, just to make this fun. Mass, right? Since it's a scalar, you'd simply say 20 kilograms. But what about your weight? Your weight, for you to find your weight, you'd have to take that mass and multiply it by the gravitational acceleration, which is 9.8. Then you would find it should be around 200. Let's say 196. I think, yeah, somewhere there. 196 newtons, right? That is weight. If someone says I weigh 20 kilograms, what they're actually saying is they weigh 196 newtons. So that's the difference between mass and weight, but you will learn that later on, not now. Now, so force is also an example of a vector. Another example, let's try this one, black. Another typical example of this is displacement. Oh, I should have put it there actually. Should have done this. I forgot to mention that an example of a scalar distance, right? While they can say 20 meters, for instance. While we have displacement. Displacement is also measured in the same SI units as distance, but they do not mean the same thing. E.g., 20 um, 20 meters north. Can be any direction, north, south, west, east, southwest, south, north, I don't know. Okay, there's no such thing as south, north, but southwest, northeast, and so on. Right, so that is displacement as an example. So displacement and distance are not the same thing. Always remember that. Right, so for example, if you right now, you move from, let me show you a quick example of how distance and displacement actually are not the same. This is point A, this is point B, right? Stay with me. So if you move from point A to point B, and let's say that they are about 20 meters apart, that would be the distance, right? And then let's say after moving from point A to point B, you then again go back to point A. Now, one would ask you, what's the distance that you covered during this whole trip? You started from A, you went to B, and from B, you came back to A again. So that means 20 meters going, 20 meters coming back. So that is a distance of 40 meters because it's 20 meters going and 20 meters coming back. Now, let me show you how displacement is different. With displacement, if you go to A, let's say going to A is your positive direction. Displacement follows the same way you would write a Cartesian plane like this, right? Remember, you have, I think this is positive y, this is positive x, this is negative x, this is negative y, right? You agree? So with displacement, this is how it works. You're going from point A to point B. Since displacement has a direction, that negative or positive part of it is intrinsic to that. So moving from A to B, you'd be going positive 20. Now, when you're going back to A again, you'd be going to the opposite direction that you were initially going to. So that would be negative 20. So displacement would be 0. M, then you'd add whatever. In this case, there's no direction to a 0. Right, so that's the difference between distance and displacement. But that's not the whole point for now. I was just making sure you understand that. Never forget that. There's a difference between distance and displacement. Okay, let me see. Another example of a vector is, lastly, let's actually, I think this is the last one, acceleration. Acceleration example would be, e.g., 20 meters per second squared to the west. That's acceleration. Also remember, guys, I know some of you write it like this. I think actually most of you. It's the same as 20. It's the same thing. Don't be confused, okay? Yeah. And then, yeah, that is how you define a vector and a scalar quantity. A scalar simply has magnitude only, but has no direction, while a vector has both magnitude and direction. Right. So now, let us do a check. We've done this, we've done that, and let us go to our third point, representing a vector graphically. So you will notice that the main focus for today is vectors. Remember what we said, they have both magnitude and direction. So typically what we would do is we represent a vector as an arrow, like this, a simple arrow. Ah, right? So remember what we said, it has both magnitude and direction. So what would be the magnitude in this arrow? It would be the length of the arrow. The length. So this length corresponds to magnitude. Then the direction of the arrow. If you check this arrow, it's going to the left. Okay, my bad, to the right. No, I don't want to confuse you. In this particular example, it can point to the right, it can point down, it can point up, it can point anywhere. But in this particular example, it's pointing to the right. So that is your direction. This guy. So it has both length and direction. Okay, both magnitude and direction. So a length, obviously, they can be given any length. We can say maybe it's about 20 meters. And then that's your magnitude, the length. And then direction to the right. Good. Now that is how vectors are typically described. So like I said, they can point anywhere. And be of any size. Here's my examples. You can point up. You can have another one pointing there. Can point down. Can point there. Anyway. Okay, this arrow looks ugly. Let me use this one. Ah, much better. So in grade 10, we will only focus, I think I just made it worse. You only focus on, what's this, 1D. Then in grade 11, you will notice that these arrows are no longer 1D. They change to 2D, which is something like this. They start having angles and whatnot. You see this? That's 2D, because now you have X and Y. So, but for now, this is our main focus. Right. So that's how vectors are usually represented using arrows, and these arrows, because they have length and they have direction. You know that if an arrow is pointing that way, it means you must go that way. If an arrow is pointing to the left, it means whatever sign you are seeing there is telling you go left or go right. Good. Now let's move. Mm, Let us move. Another definition I want us to focus on before we move is that vectors can be added to one another. I'll show you what that means. Either graphically, I'll show you what that means as well, or algebraically. I hope this algebraically of mine is correct. Braically. It looks fine. If you're into English and all that, please check my spelling there. But other than that, we should be fine. And then now, so when you add two vectors together, adding two or more vectors together, you get what we call a resultant vector. Right. Whenever you add two or more vectors together, you get a resultant vector. So a resultant vector, what it's telling us is that if you have two or more vectors, let's say they are going in the same direction, you can literally describe both vectors using one vector, and that vector is called a resultant vector. So let me define a resultant vector, then we can start making examples. It's basically a single vector that has the same effect as all the other vectors combined. I'll show you what that means. Right. Now, the big question is, how do we add vectors? How do we add them? Okay. So the way you do it, we use what we call method. We use what we call a tail to head method. Now, before we get into the specifics of what this method looks like, let me show you. If you have a vector, let's see if I can do this. Right. If you have a vector, that's your vector. Right. Remember, we said a vector can be represented by an arrow. So you have a vector. This would be your tail. And this would be your head. Right. So if this is your tail and that is your head, how does the tail to head method works then? Now, the way it works is, imagine we are given a force and we are told that, let me say a quick example. Right. Two forces of 50 and let's say 20n respectively, are mm, are something like this. So you have two forces, 50 newtons and 20 newtons, and they are both applied to the right direction. Now, what is the resultant of these forces? So, a quick principle, whenever you draw vectors, you would start by any of them, even the 20, even the 50, start by any of them. Right. Let's say we start with the 50. You represent it using an arrow, right? That's your 50 Newton vector to the right or east. If you still remember your compass, this is east, that's north, that is south, and this is west. Right. If you have these two vectors, we are told that they are both going to the right, or they are both applied to the right direction. So what you do is the second force, you first write this one, is 50n, right? And what about the second one? Where do you write it? So the way you do it is you always start the tail of the second vector, or the third vector, or the fourth vector, or whatever vector you have there. You start it at the head of the first vector or previous vector. And you draw it going wherever it's going. In this case, we'll make the arrow shorter because 50 is smaller than 20. We're not drawing to scale for now. Right. So this is the representation of these two forces. Let me say, I want this to be on the same page. Let's see. Let's do this so that you don't lose sight of this. Right. Let's put it there. Now, so if you have this, right? Now, what I was saying, let me highlight it. Always start the next vector from the head of the previous vector. So the tail is not complete. This statement is not complete. You always start Yes, this one is much better. And also, for the sake of making sure that we see the different vectors, let's make the 20 Newton vector a different color. Right? I just erased my work. Jesus. Now, so the principle of a resultant vector is saying I have these two vectors that are going somewhere, and I want to find what is the resultant. Remember what we said about the resultant? It's basically the sum of all these vectors, such that its sum represents the overall effect of these vectors individually. It's like saying, I know that if I take 10 people and I have them lift a 200 kilogram car, right? It means that all these people individually, assuming everyone works together, all these people lift about 10 kilograms each, right? So a resultant now comes and says, instead of all these people lifting 10 kilograms each, I will just come single-handedly and lift all the 200 kilograms by myself. So that's essentially what it does. So how you calculate it or how you find it is using the tail to head method. What does it mean? So now you have these two things, right? Let's put it here. So the resultant, you draw it from the tail of the first vector. This is our first vector, vector 1, vector 2. You draw it from the tail of the first vector to the head of the last vector that you have. So what you would do is you would just draw it from, let's say, which color I can use. Let's say I use orange. You draw it from the tail here, right, to the head there. So that would be your resultant vector. But the issue with drawing it like this, you can't see it because now there's a lot of arrows happening. You can't see it. So what you do is, you know that if I do a dotted line like this and I draw something here, they're basically in the same position. And also if I come here and make sure that it doesn't go up beyond that point, I know that it'll be at the head of the last vector. Then you draw it. That's your resultant vector. Now, how do you find its magnitude? So since these two arrows are all going to the same direction, it simply means you must add them up. So if you add 50 plus 20, you get 70 newtons. Now this right here is your resultant vector. We'll make another example, don't worry. So, quick notes. Is drawn tail of the first vector to the head. Notice I didn't say to the head of the second vector because there can be so many vectors we are adding. I just said to the head of the last vector because saying that is more universal, right? Last vector. You don't say to the second or third or because you never know. You can have as many vectors as possible. So let's label it. I want to label it. So let's say yes, much better. This is our tail. Tail of the first vector, right, is this one. Head of the last vector, that one. My pen. My pen is misbehaving. Aha. So that's how you would draw a resultant vector. Good. So at this point, we've used the force vector as an example to show the equality of vectors. Okay, we haven't done negative vectors, but we have done the addition of vectors in one dimension. So let me show you what it means to have a negative vector. It's basically the same thing. So what happens is, now imagine Right. So imagine now the 20n vector of force is applied to the west or to the left. We still have the same situation, but now the 20n vector changes direction. It's a separate scenario. Paste. So instead of having it going that way, now it's going the other way. Remember what we said, whenever you draw these vectors, what do? You place the tail of the next vector, which is the 20n vector in this case, to the head of the first vector. So you place the tail here and then throw it that way. But you can't see it like this. You can't see it. It's a lot of arrows now, even though it's just two arrows. So what you do, the same principle that we did here, you create a line here. You know that this line basically marks the start point or the end point of the head. So I'm basically in the same position. And then you draw it going that way, because now it's going to the left. Right. So now, how do you draw the resultant? So this is 20 in. You say the resultant is always drawn from the tail to the head. Hence, it's called, I forgot to say this. I don't know why I'm forgetting things today. Hence, it's called tail to head method. because it's from the tail to the head. So now imagine if you had the 20 Newton force applied to the left or west. Now you have a separate issue now. So this is probably the last example for today. I don't want to overwhelm you because you haven't covered this chapter already. I will cover it in more detail again. So now, imagine you have this 20 Newton force applied to the left. Let's put it here. What do you do? The two vectors are now in opposite direction. As you can see, one is pointing to the left, the other is pointing to the right. That's an obvious thing, right? I know, I like stating the obvious. It makes your life very easy. Vectors are now in opposite direction. So before you add them up, choose your direction that you would call positive and stick to it. How do you choose this direction? You choose it randomly. You don't care really. If you feel like today you want to choose right as positive, that's up to you. If you want to choose left as positive, that's up to you. What I usually do to make my life easy, I choose, if I see that in this case, let's make this case as an example. I know that the 50n vector has a greater magnitude than the 20n one. So I'll choose its direction as positive so that when I add them up, I get a positive answer at the end. That's like saying if I have negative 20 and 50, and I want to choose which one is positive, I will choose the 50 as positive. Right. So let's say we choose 50 as positive. It doesn't affect anything. Even if we chose 20, it doesn't matter really. I just say we choose 50. n, no, not 50n, sorry. Say we choose right as positive. Right? Now, that is just the admin of it. But the principle stays whenever we need to draw the resultant vector, we draw it such that it starts at the tail of the last vector, of the first vector, and ends at the head of the last vector. I don't know why it looks like 2 on. It's actually 20. Sorry. 20 newtons, not 2 on. I don't know what that 2 on is. So now, once you have that, sure. So now once you have that, say, tail, head, head. From the tail of the first vector, this is vector 1, this is vector 2. Okay, let me label them using a different color. Now it looks fun. To the head of the last vector. So remember, we can draw our little thingy here to make sure they start at the same point. This is me saying I'm drawing from the tail of the first vector to the head of the last vector. Aha, that's my resultant. The resultant is drawn like that. So now, remember, we chose a direction and we said left is positive. So when we add up these magnitudes to find our resultant magnitude, what we do is resultant will be 15. If you notice, my 50 will be positive. Why? Because the right is positive. Let me do this. Chose right as positive, and therefore this guy. Meaning left is automatically negative. Let me reduce this. If you choose one direction as positive, it means the remaining direction is automatically negative. So when you add them up, what's happening? Right. Left is automatically negative. So let's write it. So when adding them up, you write plus, then you add up your, remember these are vectors. They have both magnitude, which is 50n, and direction, which is my positive or negative in this case. So positive, we said is right, negative is left. So minus 20n, which is my left. All right. So when you add this up, you can just punch it in your calculator. It will give you 30 newtons. Since this is a vector, we specify direction left. Right. How do we know it's right? There's a positive sign here. Remember, we chose right as positive. Therefore, since this answer is positive, it means our thing is going to the right. Good. That's what it means. So this is how you do vectors in general. Right. There's quite a number of examples, but for the sake of today's lesson, I think we should leave it here so that I do not by any means overwhelm you. But we've covered quite a lot. I mean, we've just done everything up to this point. We've defined a resultant. We've shown how to deal with negative vectors and how to add vectors. And then we've also shown how to determine the resultant vector graphically using the tail to head method. Right. We haven't done more than two vectors yet. I think we can do it on the next lesson. For this lesson, just to make sure you have the brief idea of what vectors are, let's leave it here. We will do more on our next lesson. So let's leave it here for today. Let's leave it here for now. We'll cover more on the next lesson. So just to recap, quick recap. We defined scalar quantities, but before we got to that point, we said in this physical reality that we live in, we have what you call physical quantities. Basically, they can be measured, right? And then we said any of those physical quantities, if it has a magnitude only with no direction, it means it is a scalar. But if it has the magnitude and the direction, it means it is a vector. And we made examples of vectors, speed, velocity, and so on. No. Velocity, force, displacement. We made an example of scalars as well, speed, mass, distance, and so on. And then we learned about that a vector can be represented using an arrow. Can be any direction, up, down, left, right, east, west, south, north, and so on, right? And we also learned that vectors can be added together, either graphically or algebraically, right? And for today's method, we sort of learned both in one example. By graphically, we mean using the tail to head method. That's graphically. While by algebraically, we mean adding the numbers and choosing a positive or negative direction. Right. So that's how you would do a head to tail method. So what I want us to do on our next lesson, we can talk about scales and whatnot. Because when you draw this vector, right, this vector, you might find that you're using a ruler, just drawing it on your exercise book, and you are told that it's 50 newtons. If you want to use the graphic method, you would have to use a scale. So you'd say something like 0.5 centimeters on my ruler is equals to 50 newtons, something like this. So that when you draw a vector that is about 5 centimeters, you know that vector is equals to 50 newtons. But don't worry about that for now. We will cover it on our next lesson. So yes, we've added two or more vectors. We've done, I think we've done a considerable amount of work. And then by the time your teachers cover this content, you should be at least confident that you know what you're doing. Great. So thank you very much, guys. I will see you on the other or the next lesson. Yes. I think for now I can stop sharing my screen. I see there's still people in the call. You guys can log off. We are done for today.